Can you hear me?
Yes, sir.
Okay, fine. So let me start. Okay. See, we have almost reached the last topic, that is the applications of Smith chart. And today we are going to discuss one of the very important topic, that is single step matching. In the next class we will go for double step matching using the Smith chart, how to do that. Okay. So and definitely you can expect from single step matching or double step matching, any one topic will come in the exam. So if you understand single step matching, then only you can understand the double step matching. So whatever the questions you have in mind, you can openly ask, and better you buy Smith chart and practice that. Some students asked about workout on the real Smith chart. I am doing that process. So whatever the examples today we are going to, which one example we already have seen, we will discuss about that. Another one example also I will show today. Both examples, real workout, Smith chart workout should be. I will upload that. Okay, in Teams itself I will do that. Yeah. So we discussed about transmission line theory and how it is evolved. All these things already discussed a lot, and up to this transmission line one, that is the module 6, I think, that is discussing about the primary and secondary parameters of the transmission line, which describe the modeling part. The second module describes the impedance of the characteristics impedance and the input impedance of the transmission line for a given length of line. All these things we already discussed. And so this what is the advantage of studying this is, like, we can construct so many circuits using the transmission line itself, particularly matching and then creating reactance at a particular wanted place, or in order to stop a particular signal we can create reactance to cancel the particular signal. All these things can be done with us within the scope of transmission line. So that is why most of the high frequency systems are developed using transmission lines itself. In the after double step matching, we have around 3 classes. In those 3 classes, one class I will take exclusively on how this transmission lines are useful for the uh, various applications. Beyond that, uh, so-called matching network, there are so many applications like filters we can design, amplifiers, so many things we can design out of the transmission line concepts. So we already discussed why Smith chart has come to solve so many complex uh, calculations related to impedance and the reflection coefficient. They have come up with a normalized version of drawing the reflection coefficient as the function of the reactance, real part and imaginary part. So there comes the real circles and the imaginary circles. Combinedly, we have the complex circles or complex impedance circles. And so this impedance chart, which we regularly means which we call as a Smith chart. So this is the Smith chart which you see actual look like. And if required, we can take particular part and we can work out. Okay, that is up to us. Then what is the advantage of having this Smith chart? Like, we can plot so many things. Like, we can map the impedance, we can map the admittance, we can map the reflection coefficient, we can map the so-called VSWR. So many things actually we can plan. And in fact, these are the four important in the sense, almost these covers 90% of the description of the microwave circuits. So that is why microwave circuits often use Smith chart to solve so many problems. And in the Smith chart we can move around with respect to the transmission line length. So this is the load impedance, and from the load impedance I want to calculate the input impedance at this particular location. For this we generally use this equation. Generally we use, but every time calculating the same values for different, so it will take time. but rather in the Smith chart with one simple move from once we have placed the ZL, we have to simply move over according to the electrical length. So once the frequency is known, we are going to calculate the lambda, and total whatever the length, we are going to divide by this value. So whatever the value of length, we will get in terms of lambda. So let's say we will get 0.5 lambda like that. 0.5 lambda is nothing but lambda by 2. So you can move around lambda by 2. Lambda by 2 is the one full length. So lambda by 4, lambda by 8, like that we can easily move around. And we can, so whichever the point you are looking at, so this is nothing but the input impedance at the length L. We can easily calculate. So, so there are some procedures available. We already discussed about this procedures. I believe we have already seen how to map the impedance, all these things. I will skip these parts. Now we will move to the applications of the Smith chart. Okay, so the first application of the Smith chart is we can calculate the reflection coefficient input impedance for any particular circuit, particularly whenever there is a load, and after the load at a particular length L, here the length is 6 lambda by 4. What is the input impedance? Similarly, what is the reflection coefficient? Everything we can calculate with single points. We can easily calculate that. In fact, this need only one basic thing, that we have to normalize the impedance. So that is the first thing we have to do. And when we finish the work, we have to take the impedance value and we have to multiply with so we will get, let's say, small input impedance will come. We have to multiply with Z0, so that we will get the real impedance value will come. So till then, within the Smith chart, there is no unit available. Everything is simply numbers or simply complex numbers. And we can convert from impedance to admittance just by going diagonally opposite point. We will get the admittance. So, and the another very important application, what is today's topic, is the single stub tuner. So what is single stub tuner is nothing but we have good impedance matching networks, like for example we have quarter wave transformer that can solve only for real part alone. But if we have some complex impedances, many circuits in microengineering is actually complex ones. For example, transistor, diodes, and then antenna, and we have modulator, demodulator, many circuits. And in fact, very some advanced structures like mixers, multipliers, then power dividers. So many circuits are there. So these circuits are generally having their impedance as a complex system. So if it is complex system, it is very difficult to solve both real part and imaginary part. So how to solve that? So ultimately what we want, we have ZL. So this ZL has the real part RL and imaginary part as the XL. So RL plus JXL, that is nothing but ZL. Okay, so this ZL we have to match with this value, where the value is Z0. But this is, you should remember that this only has the real value. So what we have to do, we have to map the real part to Z0, and the XL part should be cancelled. So that is what we are supposed to do. So how to do that? So for this, we are actually having a simple method, that is what we call as single step matching section. So what is the procedure for it? Let me erase this. So you have to understand this principle, so that you can, in fact, you can solve the Smith chart problem by yourself. It's a very, very simple trick. Okay. Okay. So we already know that this is a load impedance which has a real part and the imaginary part. So real part and imaginary part we have. So what we are going to do, we already know that whenever we move this ZL over a distance, you will get changes in both this part. So what we are going to do, we are supposed to move this particular point such that at this particular point, the real part supposed to be equal to Z0. So we have to move for a distance of D here over this series way. We have to move over the transmission line, whose characteristics impedance is Z0. It is also can be referred as a Y0 as a admittance, characteristics admittance. So over a distance or over a particular direction, sorry, over the distance d we are moving, and we will get the value of Z0. So this real part and real part is matched using this position, but by the time this XL will become XL dash after this position. So we have to cancel that. So how to cancel that? I am going to add its corresponding opposite one. So minus XL I am going to add. So how to add? We have to place a parallel stub. So we can place a parallel stub of either open circuit or short circuited stub. We already know that open circuit stub will give capacitive and short circuited stub will give this inductive. So if this is actually negative, we can solve by capacitance. If we get negative, we will get the value, sorry, if we get the value positive, we can solve with the inductance. Like that actually we can choose ourselves. So by doing this, we are going to cancel out this reactance part. So the reactance term entirely will become 0. So what we can say is at this particular point, we will get the input impedance is equal to Z0 plus J0 will be there. And this transmission line has Z0, this also has Z0, both match each other. So the problem is solved. So that is what we are going to do. And how to do it in the Smith chart. So the very first thing is we have to map the ZL. So ZL we have to normalize by Z0. You will get small ZL. This small ZL should be mapped first. So here you can see that, assume that this is the point, small ZL, and we have to convert the entire problem in the admittance mode. Then only we can easily parallelly we can add. Otherwise, this in the impedance chart it is very difficult. So we have to convert this to admittance part. Admittance part is very simple. We need not to do anything. We have to simply move this ZL point to YL point. So how to do that? We have to go diagonal. So with respect to the center, we are going to draw a line. It will reach the other part of the circle. Okay. So the circle, how we draw that? We have to take the compass, and with respect to the center, with respect to this impedance point, we are going to draw the circle. And I think all of you know that this is nothing but SWR circle, commonly referred as S circles. Okay. So we got the YL point. This YL point we have to move. So where to move? This YL point is supposed to be moved such that it will reach the value of Z0. Z0 divided by Z0 is nothing but equal to 1. And we have to find this. So here the normalized value is 1. And interestingly, this Y0 is also equal to 1, because 1 by 1 equal to 1 only. So, and we have to find the real circle which is having the value of 1. So we already know that the one which is passing through the center is nothing but the admittance equal to 1 circle. So this is that circle, and in many of the books it is referred as the unit circle. Okay, so in fact before the exam itself you can very well draw the unit circle very well ready, because you need not to search for that later on. You need not to spend the time upon that. Okay. If pencil or something else is there, you can make it, or even with sketch also you can do that. Better you buy a better high quality Smith chart. If you have some other colors or something, you can better you do that. At least some 3 to 4 chart you can keep for exam, and keep this unit circle ready. It is very useful for many purpose. In order to identify where one is available for that purpose, it is very useful. So now our job is to move this particular point to reach the unit circle. There are 2 places it can meet. One is this particular point, and this is another point. We always try to go to, you can see this, the admittance is positive now. We have to move to negative value here. If your admittance point is here, let's say, you have to move up to here, like that. So you just keep this in mind. or you can also reach the point here also you can reach, nothing wrong in it. Theoretically it is not at all a problem, but practically there are some issues available. That is why we always try to take the opposite side. You can also take the nearest side. Okay. So what we are going to do, we are going to move the circle along the circle and such a way that it reaches this particular point, and this is the point. You will see that the value of the admittance is nothing but 1 plus j, sorry, there is 1 minus j, is it? Because it is in the it is in the negative side, in the bottom circle, the bottom half circle it is available. So it is nothing but 1 minus j jxl. Okay, so we have to cancel out this reactance. So how to cancel the reactance? We have to choose this particular point. This particular point will be having positive value. So we have to choose this point and we have to move over a distance up to this. That is the value we call d. So this distance d is nothing but this moving. So how to find out the value? We have reference value. For instance, this value is coming at 0.14 and this particular point reaches at 0.32. Find the difference. So that is the total distance of this value d. It is always we have to represent in terms of lambda. For instance, 0.32 minus 0.42 will give approximately 0.28 lambda. Something like that we have to place. I think it is not correct. I think it is 180. Okay. Now we have to cancel this value. To cancel the value, we are going to opposite side. We have to move along the imaginary circle because we have to cancel only the reactance part. Then we have to mark this point. From the center you have to take the line, and here you can see this value is 0.16 lambda. So that is the length of the open stub, which is nothing but 0.16 lambda. So that is the answer for this particular problem. So let us take an example so that you will understand quickly. This we already have seen. So this is the load impedance which is available here. Then we have to create the stub, single stub. So sometimes it will be mentioned that what type of stub we have to use, whether we have to use short circuited stub or open circuited stub. So here it is mentioned short circuited stub. Then we have to match with the 50 ohm line. So we have a 50 ohm line here and we have a load impedance here. What is our job is we have to find the distance d and the stub length L. So these are the two things we have to do. So what is the first thing we have to do? We have to take the ZL, we have to normalize with the characteristics impedance 50 ohm. So this value become like this, and this value we can't say that this value will be going from 0 to 1 like that. There is no limit. Impedance value can range from 0 to infinite. We already know about that. So ZL value, this ZL value should be mapped in the Smith chart. So for this you have to find R equal to I suppose to use small r. So R equal to 1.2 and X equal to 1.6. So here you can see this value is 1, 1.2 is here. So this 1.2 is the R value. So for that corresponding circle will be there. So you have to follow this circle. And for 1.6 also separate circle will be there. Where to find the 1.6? We can see that this is the value 1, 1.2, 1.3, 1.6. So this 1.6, with reference to that, we have to draw a line like this. Slowly we have to move, and this 1.2 circle and this 1.6 circle, they are meeting each other at this particular point. So this is our ZL point, and it is noted as point A. So you can note the point as ZL itself for convenience. It is up to you. So this point is taken. So this is our first reference point. Now the second step is we have to find the YL value. So how to find out the YL value? We got the ZL point here. Then we have to find the YL point. We already know that it is diagonally opposite side. So it is diagonally you have to go opposite to reach this. So we have moved diagonally opposite to reach this point. So this particular point is nothing but YL point. So we even need not to calculate all the time whether it is correct or not, YL is correct or not, like that. You can easily get it. So YL point is reached, and thereafter you have to forget this one. Okay, you should not keep on pinpoint that this one. Okay, we have to forget this. Now YL point is there. So this is our primary reference point. Now this point supposed to be, this YL point has Y real part plus J XL imaginary part. So this I have to move to y equal to 0, sorry, y equal to 1 circle. So where the y equal to 1 circle, here you can see that it will be, most probably it will be very much visible. So it will be a bit thick also. So we have to identify that circle and we have to draw that. So you need not to draw that purposely, but if it is already available with you before the exam itself, you can keep it ready. So now you can see that this is the YL point, and this is the point where this VSWR circle and the unit circle is meeting. We are supposed to move this particular point from here to here we have to move. That is our job. So in order to move that, we can't simply move, we have to move according to the electrical length lambda. So for this, we are actually going from here to here. So you mark this point, always you do like this, like with respect to the center you put a point, and this is the point of reference. Then you draw a line such that it go outside the Smith chart. Outside the Smith charts also, you will find some space, you just go up to there and exactly find where the value is available. I believe you can see here 0.06, here you can see 0.07. In between we have to find the value. There will be 5 divisions, each division is 0.002. So after the third division we have the value. So 0.066 plus 0.001 I added, so I got this value. So that is how I have pointed out. It may be accurate, it may not be accurate, but you have to use your basic scaling idea and you can map it. Then we have to come to this YL point, sorry, unit circle point, and we have to extend this line up to here. So this point I have to find. This I can see that it is 0.17. This point is very close to 0.18 and slightly after that. So I have taken the values 0.181 lambda. Okay. See, if you put the value 0.180 also, it is nearly correct only. So you need not to worry about that. But always try to use 3 decimal point, because that is very, very important. Here also you can see that it is used with 3 decimal point all the way. Always you do like that. Now we have to find the difference between that. So take the value 0.181, this is the problem, 0.067 lambda. When you find the difference, you will get the length. So this is nothing but the D, the position of the stub from the load. Okay, or the distance D, like that it is called. So we got the value. Now we have to cancel the reactance at this particular point. So for that we have to choose exactly opposite point, this particular point, not this one. Remember that. So we have got this particular point, opposite point. So this point only going to cancel our reactance. So how to map it? So you can see that, let's say this particular point is here, then you have to follow this particular point. Then slowly you have to extend up to here. You should be a bit careful about moving this. Okay, so then you can mark this particular point. Same way it is done over here. So slowly it is marked and reach this particular point. Don't take any like a compass or something else to do that. You're supposed to do it by hand. Okay, we can see very well that students used hand or some other instrument to do this work. Okay, it's supposed to be done by hand. There is no other go. and you can easily do that, and you will reach this particular point. Now this particular point we have to draw from the center like this. So we are drawing from the center, and it reaches, go up to the outside the Smith chart and find the electrical length. Now the question is, what is the length of the short circuited stub? The short circuited stub length will be calculated with respect to this particular point, which generally has the value of 0.25. And if it is asked with open circuit point, you are supposed to choose this point which is having the electrical length of 0, from 0 to this value. So that is open circuit point. And for short circuit point, from here to here. So like this is 0.34, 0.35, in between 0.345, and this value minus this 0.25. So that is nothing but the short circuited stub length. So it should be given clearly that it is a short circuited stub. Like that you have to close that, and you mentioned that it is a short circuited stub. Simply you can put short circuit like that. Otherwise, if it is open circuit, you calculate from here. So 0.34 minus 0, directly this value you can write, that is the open circuited length. So both the answers are correct. So finally, what is the meaning of it is nothing but, so you got the ZL, and at this ZL point you got ZL is nothing but RL plus JXL, and at this particular point you got R0 plus JXL, and this short circuited stub is going to give minus JXL. So this minus JXL and this plus JXL, they will cancel each other. Finally, when you look at here, you will see only this R0, and which is going to be Z0. Therefore, the system is matched. So how to check whether it is, how to check it is matched or not? If you calculate the input reflection coefficient, you will get the value of 0. So for this, I have done a simulation. So this simulation I already told in the last class itself. I got the result. So this clearly tells that, so the reflection coefficient is very sorry, this is actually approximately equal to 0. Now we will take another example. Quickly we will finish that. Then if you have any question, you can now ask upon that. Now there is an antenna. The antenna has an impedance of this value, and it should be matched with the characteristics impedance of a lossless line of 100 ohm. So here Z0 value is keep on changing. So there is no fixed value for Z0. It will be completely depends on the type of transmission line. So now it should be done with a shorted stub. Okay. So we already have seen the for shorted stub, but we will do for both stubs. So open circuit stub, short stub, everything we will see. So these are the list of things you're supposed to do, and which is all asked here. So first we are actually normalizing the impedance. So we are taking the value and divide by Z0, and you got the value. So this is R circle plus J X circle. So we have to locate it. So first we are finding the R circle, which is 0.4. This is 0.1, and this way it will keep on decrease. So we find out this 0.1, and we are going to extend this particular point. Then 0.3. 0.3 is plus 0.3. So we have to find plus 0.3, and we have to move over this. So we got it. This two intersecting point. This point is nothing but the ZL point. Remember, this is the same point called gamma L, the load reflection coefficient point. So now the next step is we have to calculate the admittance for it. So how to calculate the admittance? We have to go diagonally opposite. So for that we have to draw the VSWR circle. So how to draw the VSWR circle? Keep the compass one leg here, the pencil point here, and draw a circle. So that is the VSWR circle. And if you go diagonally opposite, you will find the YL point. If you calculate the YL point, you will easily get it. So you can cross check that. Now this is our reference point. So here after this point I generally don't use. So this is the YL point. Now we have to move this point. You're supposed to remember this. Always you have to move along the clockwise direction. This is actually very important problem. Many students, those who are studying the transfer line theory, several times when they do that, they get this question all the time. The very fundamental or simplest method of the single step matching uses clockwise direction. There are some problem uses anti-clockwise direction, which you need not to confuse now. So always you go with the clockwise direction. So when you do clockwise direction, you have to go like this. This is the admittance point, and you have to follow this circle, and you have to move up to this G equal to 1 circle. So this G equal to 1 circle, you already know that where the admittance is equal to 1, that circle. So both are meeting at this particular point, and this distance we have to calculate. But if you remember that, if you see that this one line is in the negative half circle and one is in the positive half circle. So this is a little bit tricky one. So how to calculate that? For this, you have to follow a simple method. So with respect to the center, we already know that this is going to be 0 lambda. You have to move along that 0, 0 0.001, 0 0.002, like that. If you follow that, you will see that this line is actually meeting approximately at 0.197 lambda. Okay, so you mark the value, and this side when you move, you can see that 0.001, 0.002, 0.003, like that. It is reaching another point here, and this particular point has the value of 0.164. Now the total distance from here to here, we have to add this. When you add this two value, you will get the total distance. So this is the position, this is the distance we supposed to move the impedance point to cancel, to make the so-called admittance equal to 1, or the normalized resistance value as equal to 1. So that is what we have done here. Now we have to cancel this. So in order to cancel this, we have to go opposite side. So we are actually moving to the opposite side and meeting this particular point, and we are going to draw this line just up to the edge. Now this particular point, if you notice here, this is 0.033, this is 0.034. So in between some value, so that is 0.332, 0.332 lambda. And there are 2 points. This is referring the open circuit point, this is referring the short circuit point. And now I am going to do with open circuited stub. So for this, I am going to take this 0 lambda as the reference and calculating this. So it is very easy that my final value is 0.332 lambda minus 0 lambda. So that is the value. So that is going to be the open circuit stub length. So the final answer is here. So this is the D value, and this is the open circuited stub length. So in I generally use LP, that is position of the stub, and LS, that is the length of the stub. So I have used this, but according to the book you can follow, this is D, this is L. That's all. So we got for open circuit stub. But this is one of the solution. There is another solution is possible. What is the second solution? We are going to take with respect to the short circuit points. When we take with respect to short circuit point, we can reach this particular point. So this short circuit has reference point as 0.25, and this is the stub, this is the final location. We have to find the difference between that. So we got the difference, and this is the short circuited stub length. So the same point D will get different L. So this value is 0.0. So you're supposed to cross check what type of stub being asked. So you can see here, this in this question it is clearly mentioned, design a short stub or shorted stub, short circuited stub, or simply short stub, like that. Multiple names it is always be called. So it is very simple. You can note down as a short stub or short circuit stub. So here it is asked with that. Some question will be asked with open circuit stub. So you have to be very careful about that. So you've been taught with both. This is the answer for single step matching network. So finally, when you look at the impedance here, you will get Z0 value. So that is the final answer we want. So if you have any questions on this particular two set of problems, I'm ready to answer for that. You can see that for explanation itself, I took only 15 minutes. So you can easily finish it in less than